So we went ahead and printed a whole bunch of TPU dog bones and ran them through our very expensive tensile testing machine in order to find out how strong our 3D printed parts when actually printed. Now let's do some context for this test. Now we're using standard dog bones that we've used before in all the other tests. Our tensile testing machine applies a constant force over time until the parts break. Now, the very first issue that we ran into is the fact that TPU is soft. In order to do a useful test with 3D printed parts, the strength of the part laying flat isn't really relevant. In all past research, the strength of a part laying flat is about 90% of whatever its normal isotropic nature would be. There's not really any effect that 3D printing has on a part in the X and Y direction. However, layer adhesion, the vertical, the Z direction, that is where 3D printing is different. The layers stacked on top of each other is where 3D printed parts fail because there is a weakness in that direction. So we print the dog bones in all of our tests vertically. Down the line we'll do some more. Make sure you subscribe to the channel, but this is the relevant test that has the most information and is the least understood. But we're printing TPU, and if you haven't heard before, TPU is soft and these are tall and thin. So we gave it a shot. We tried to print these dog bones out vertically without any additional supports or redesigns in order to support them as they went up, and it went about as well as you would expect. The dog bones came out very rough and nasty. We did get them all out entirely, but to be fair, within these tests, they're not very accurate tests because there are stress concentrations from blobbing and wobble and all the rest of it that aren't really fair. However, all that being said, the test results are still really interesting, and we'll talk about that a little bit more. So going into it, we had all these dog bones. We had 30 separate samples that we wanted to test in order to get as much spread of data as we possibly could to make sure that we were catching all the situations. TPU itself is a thermoplastic urethane, which is a group of polymers that are really useful. And TPU is an amazing material. It is really chemical resistant, it is very heat resistant, it has really abrasion resistant, and it has pretty good properties when printed. It can be difficult to print with though, so the challenge with that is learning how to print it. You generally have to print with the direct drive extruder. Bowden machines won't ever be able to do it. Now the material that we were actually using was Overture TPU, and if you want to get some of it after these tests, you can go ahead and find the link down in the description so that we get a little bit of a kickback from this, effectively a review telling you about the material. So please help us out on that one. But this TPU had a 95A shore hardness, which is about as hard as you can get commercially generally without adding something really specialized. But TPU goes all the way up to the hardness of a hard hat and all the way down to the softness of like a pencil eraser and the stuff you get all the time. 65A is about as soft as you can get on a traditional type of machine without getting all kinds of problems. But if you have a good machine that's optimized for TPU, then you can print that reliably too and go even lower down to like 30A. But let's go ahead and get into the tests. So like we said, with all of these tests, the dog bones were defective. They had overextrusion and wobble throughout them. When we made a slight mistake in this test in not considering how much elongation would occur with these parts and how much it would affect the actual clamping of the parts. So even though we got tests out of them, not all of them are as consistent as an ASTM test would be. So we have to redo this at some point. But again, this data is really useful as it is. Across all of these tests, we always ended up with a maximum force between 200 and 400 newtons. Now, that is on average about 70 pounds of force if you're over here in America, which is not a lot. But if you actually look at the tensile stress of these parts, you end up with a range of between 4 and 8 megapascals. And this is interesting because even though these parts were 3D printed and the layers are having to stick to each other, the actual tensile stress of this type of TPU is actually expected to be about 8 megapascals. So within our tests, we are able to reach 100% of the strength of an isotropic material, even though it's 3D printed and the layers are having to stick to each other. Now, of course, the lower range of those data points is not good because you don't want it to be down there. You also don't want that much spread. But a lot of that is attributable to how much the samples were just wonky because they're a tall, skinny noodle trying to be printed on. The way we will improve this in future is rather than printing just a grouped stack of dog bones, we will basically put small ribs between the dog bones so they support each other as they're being grown, so that you maintain really high dimensional tolerances and reliability of the layer lines of those parts growing up. But that's a whole different, effectively a designed sample specifically for this material. And starting out here, we want to be able to just knock out these materials. So the more rigid materials like PETG, ABS, PLA, none of them have this sort of printability problem, which TPU does because it's so soft. But if TPU is appropriately processed, it looks like it is as strong as itself even after it's 3D printed. And printing doesn't really radically affect the strength in the Z direction of a TPU part. And this is not that surprising. Here at Slant 3D, we do all kinds of mass production of parts, and we always harp on using TPU because it's so darn durable, so darn strong, and is chemical resistant and has all these other features. It also has a lot of really good UV resistance. So manufacturers actually should make a rigid version of this, and they don't because since TPU is compressible, it's actually quite difficult to process and turn into filament, because when you can squash water, it's really tough to make it flow out of a nozzle in a consistent way. So this is the challenge with creating TPU filament, which is why its cost can be higher, but also the value of creating TPU filament, because it has all of these material benefits that allow it to be really reliable even after printed, so that you can do good quality engineering and predict how this material is going to work without having to worry about it degrading because of the process that you were using. So a 3D printed TPU part looks like it can pretty much be as strong as a pure injection molded part, because you can't be any stronger than the actual material spec itself. Have a great day, everybody.